Select the major product of the following series of reactions. So we are starting this series of reactions with aniline, an aromatic amine. And the first thing that we're doing with this aniline is we're going to treat this with a solution containing sodium nitrite and hydrochloric acid, and we're going to be careful to keep this solution at around 0 degrees Celsius. So what this is doing, the sodium nitrite and the hydrochloric acid are reacting to form nitrous acid, HNO2. And the nitrous acid is not stable, so we must generate it in the reaction mixture. And so what this is going to do when it reacts with the aniline, so we're going to do this stepwise. I'm going to show the product of each step. So in this first step, with your sodium nitrite, hydrochloric acid, and with careful temperature control to keep that at 0 degrees, what that's going to do is it's going to transform your aniline into a diazonium salt. And the mechanism for this is well known. It is many steps, so I'm not going to show it here, and I'm also not going to hold you responsible for knowing it. But here's your diazonium. And I think you can see the structure here of this diazonium is really similar to the structure of nitrogen gas. And nitrogen gas is just a nitrogen-nitrogen triple bond. So that makes this a really, really good leaving group and can be replaced by a number of different nucleophiles. So one thing you can do is if you have this diazonium salt that you formed at about 0 degrees, if you actually just let this warm up, and so I've shown it as a second step, but if you just let this warm up in aqueous acid, what's going to happen is that diazonium will be replaced by a hydroxyl group so that you get phenol. So in the next step, we're going to say that we're adding aqueous acid and heat. This really is an aqueous acid, so if you just heat that solution up with still the aqueous acid in there, it's going to react and transform this diazonium salt into phenol. So you'll be replacing that diazonium group with a hydroxyl group. And so this is the first reaction we've seen where we've been able to directly place an oxygen on the benzene ring. And so then once we get the phenol after this second step, we're going to see what we're reacting that with. So we have here a condensed structure. If we expand this out, it might be easier to see what that is. So you've got your methyl group. The carbon, the oxygen there in parentheses means that it's a substituent. So we're really drawing this as a carbonyl. That's just one way to draw a carbonyl in a line. And you have the chloride. And then you're adding pyridine in there as a base. So this is a reaction where your oxygen of your phenol is going to act as a nucleophile. So I'm not going to draw the full mechanism here, but just enough to get us to the product. So that's a nucleophile, and the carbonyl carbon is electrophilic. So this is going to attack that electrophilic carbon. We know that there's actually quite a few steps to this, that these electrons are going to come up onto the oxygen. You'll get a tetrahedral intermediate. That tetrahedral intermediate would then collapse and push off the leaving group chlorine. And at some stage in there, the pyridine would be removing this hydrogen. So this is not the full mechanism. So we're going to put the disclaimer that this is not the real mechanism, but it's enough to get us to the product. And that's a handy thing to be able to draw. So we're forming a bond between this oxygen and the carbonyl. We've lost the chlorine, and we still have the methyl group. So we've taken and made an ester is what we've done here. So now we've got an ester on the ring. And then the final step is we are treating this with bromine and iron tribromide. So that's bromination conditions, electrophilic aromatic substitution, specifically bromination. So that's going to add a bromine to the ring. And then the question is, where is it going to add it? So you want to take a look at the group that you have attached to the ring, because that is what's going to direct the incoming nucleophile. So we need to know whether this is an ortho-para director or whether it's a meta-director. So you want to look for some key structural features. And so what we see here is that bound to the ring, we have an oxygen, and that oxygen has 2 lone pairs of electrons. And those can donate into the ring. And so this is electron donating. And what it's specifically going to donate and give electron density to is initially the ortho position. And we could draw resonance structures that also show that we've activated the para and the other ortho position. So this is an ortho-para director. Okay, so we could get a bit of a mixture of ortho and para. This is a little bit sterically hindered, so I would assume we're going to get mostly para. so we can draw that product. And if we take a look at our options, we can see that this is matching to option A. Okay, so a key thing to note here, I think, is really the difference between maybe A and C, because this is an ester and this is an ester. Having the oxygen directly bound to the ring means that you've got that oxygen that can be electron donating. And so that's going to push the incoming electrophile, in this case bromine, to the para position. If we had formed by a different set of reactions this other ester, the carbonyl here is electron withdrawing. We can pull electrons into that carbonyl. And then in that case, if we were to take that ester, so just like that, and add the bromine, it would go meta.